Keeping up with our motto that learning be a joy and teaching a pleasure, here we are with the remote teaching and learning process to bridge the gap. Happy learning, students. Today we are going to continue with class 10 science chapter number 7 lenses. Topics that I am going to cover during this session are rules for drawing ray diagram for concave and convex lenses, images formed by concave and convex lenses, Sine convention, lens formula, magnification and power of lens, as well as combination of lenses. We have already learnt about the rules for drawing the ray diagram for the concave and convex mirrors. Similarly, we can also obtain the images formed by the lenses with the help of ray diagrams. So, let us see the rules to draw ray diagram for the images obtained by convex and concave lenses. Rule number 1. The ray parallel to the principal axis will pass through focus. That is, when the incident ray is parallel to the principal axis, the refracted ray passes through the principal focus, as shown over here. For the convex lens. Similarly, for the concave lens also, when the incident ray are parallel to the principal axis, the refracted ray appears to be passing through point F1, that is the principal focus. In convex lens, the refracted ray passes through the principal focus on the right hand side of the lens, whereas in the concave lens, the refracted ray passes through the principal focus on the left side of the lens. Rule number 2. When the incident ray passes through the principal focus, the refracted ray is parallel to the principal axis. As shown over here, for the convex lens, you can see this is the incident ray that is passing through the principal focus and the refracted ray is parallel to the principal axis. For the concave lens, the incident ray appears to be passing through the principal focus and the refracted ray is parallel to the principal axis. Rule number 3. When the incident ray passes through the optical center of the lens, it passes without changing its direction. So the refracted ray is in the same direction as the incident ray. It is not changing the direction. For both convex and the concave lens, it is shown over here. Images formed by convex lenses. The position and the nature of the images formed by convex lenses can be obtained from the position of the object using the rules of ray diagram. When the position of the object is at infinity, in that particular case, the rays, the incident rays, you can see over here, they are parallel to the principal axis. And after refracting, as per the rules of ray diagram, they will pass through the principal focus. So all the rays are meeting at point F. So the position of the image is F and the nature of the image is real, inverted and highly diminished. In the second case, when the position of the object is between infinity and twice F is the distance which is double the distance of the principal focus. So when the object is somewhere here between the infinity and 2F, in that particular case, you can see over here the incident rays which are parallel to the principal axis, they are meeting at the point F, which is principal focus, whereas the incident ray which is passing through the optical center of the lens, it will be passing in the same direction without getting refracted. So over here, the image that is formed is between F and 2F. At B dash, the image is formed and the nature of the image is real, inverted and diminished. In the third case, when the position of the object is exactly at 2F, in that particular case, you can see over here the incident ray which are parallel as well as which are passing through the optical center. They are meeting here at A dash. So the position of the image is at 2F and the nature of the image is real inverted and the image is of the same size as that of the object. If the position of the object is between f and 2f, as shown over here, it is indicated by AB. So, in this case, the position of the object is between f and 2f. So, the position of the image will be beyond 2f. Here you can see it is beyond 2f, indicated by A dash B dash. And the nature of the image is real, inverted and enlarged. Next is when the position of the object is exactly at f, that is at principal focus. In that particular case, the position of the image will be at infinity. You can see over here the rays are, after reflecting, they are moving towards the infinity. So, the position of the image will be at infinity and the nature of the image will be real, inverted and enlarged. In the last case, when the position of the object is between f and O, that is between the principal focus and the optical center of the lens, in this case, the position of the image formed is on the same side of the lens. You can see over here AB is the position of the object, whereas A dash B dash is the position of the image, which is formed on the same side of the lens. And so, the nature of the image will also be virtual, erect and enlarged. Images formed by concave lenses. When the position of the object is at infinity. In this case, the incident ray are parallel to the principal axis and the refracted ray appears to be meeting at the point F, which is the principal focus. So, the position of the image is at F and the nature of the image will be virtual, erect and highly diminished. And when the object is anywhere between the infinity and the O, which is the optical center of the lens, in that case, the position of the image will always be between F and O. You can see over here, AB is the original object which is placed on one side of the lens and A dash B dash is the position of the image which is between F and O. And the nature of the image will be virtual, erect and diminished. Let us see the Cartesian sign conventions for lens. According to Cartesian sign convention, the optical center O is taken as the origin for both convex as well as concave lens. The principal axis is the x-axis of the frame of reference. The Cartesian sign conventions are as follows. The object is always placed on the left side of the lens and all the distances parallel to the principal axis are measured from the optical center only. The distance measured to the right of the optical center is always taken as positive, while those measured towards the left of the optical center, they are taken as negative. It is indicated over here with the help of blue arrow and the red arrow. On the right hand side, it will always be positive. On the left hand side, it will be negative. The distances which are perpendicular to the principal axis and above it, they are taken as positive. Here you can see the distance that is perpendicular to the principal axis and above the principal axis, it is positive in both the cases, convex as well as the concave lens. Whereas the distance which are perpendicular to the principal axis but they are below it, they are taken as negative. The focal length of the convex lens is always positive, whereas the focal length of the concave lens is always negative. So these are the Cartesian sign conventions for lens. Lens formula and magnification. Ray diagram for convex lens and concave lens are shown over here in the picture. You can see AB is the position of the object, H is the height of the object, and small u is indicating the distance of the object from the optical center. A dash B dash is indicating the position of the image. H dash is the height of image. And V is the distance of the image from the optical center. And small f is indicating the focal length, that is the distance between the optical center and the principal focus. Similarly, for the concave lens also, h is the height of the object and h dash is the height of image. U is the distance of the object from the optical center, whereas V is the distance of image from the optical center. And finally, F is indicating the focal length, that is the distance between the principal focus and the optical center. Let us understand the lens formula and the magnification based on these ray diagrams. Over here, the formula that is showing the relationship between the distance of the object, that is U, the distance of the image, that is V, and the focal length, F, is called the lens formula, and it is given as 1 upon V minus 1 upon U is equal to 1 upon F. The lens formula is same for any spherical lens and any distance of the object from the lens. But however, it is necessary to use the proper sign conventions. Magnification. The magnification due to lens is the ratio of the height of the image to the height of the object. So over here it is h dash upon h. Magnification due to lens is also related to the distance of the object. It can also be obtained in terms of distance of image and the distance of object. So it is the ratio of distance of image to the distance of object, which can be given as V upon U, because V is the distance of image from the optical center and U is the distance of object from the optical center. So it is the ratio of V upon U. Power of lens. The capacity of the lens to converge or diverge the incident rays is called its power. It is indicated by capital P. The power of the lens depends on its focal length and it is the reciprocal of its focal length. So the formula for the power is 1 upon focal length, where focal length is expressed in meters. The SI unit of the power is diopter, that is indicated by capital D. If the focal length is of 1 meter, then the power will be of 1 diopter. Also, the power of the convex lens is positive, whereas the power of the concave lens is negative. Combination of lenses. If two lenses with the focal length f1 and f2 are kept in contact with each other, that is in series, then the combination has an effective focal length, that is the focal length of the combined lenses is given by this formula, that is 1 upon f is equal to 1 upon f1 plus 1 upon f2, where f is the focal length of the combined lenses. Also, if the power of two lenses are P1 and P2, then the effective power of their combination is the sum of both the powers, that is final power will be equal to P1 plus P2. One example is shown over here. If two lenses with a focal length f1 and f2 are kept in contact with each other, then the combination has the effective focal length that can be obtained as follows. f1 is plus 30 cm, f2 is minus 20 cm. So when we keep these values in the formula 1 upon f is equal to 1 upon f1 plus f2 and we solve it, we get the answer as minus 60 cm. So the focal length of the combined lens is the addition of inverse of the individual focal lengths. This is all for today's session. Thank you so much.